Hello, friends. Welcome to another edition of Science Talk with Jim Massa. I am your host and resident oceanographer, Jim Massa. And I want to discuss with you an article that was published in March of this year in the Proceedings of the National Academy of Sciences, or PNAS, as we often say for short. The Quiet Crossing of Ocean Tipping Points. This article here is really a literature review. Now, oftentimes you will see researchers publish what are called literature reviews. So it's not necessarily any new science, quote unquote, new science they themselves have done, but it's a synthesis of taken together a bunch of research that other researchers, investigators have done, and then pull it together to provide an overall narrative, a review of the topic at hand, and basically a summary of what our best knowledge of that topic under consideration is at. And that's what this paper is. So looking through the abstract, and of course, I will leave the URL link in the comments section below the video for those who want to check it out for yourselves. And you also have the option of clicking on the PDF link, and it'll kind of consolidate it for you. If I do that here, the print will become too small and it would probably not show up very well. So I'm going to leave it in this format here. So anthropogenic climate change profoundly alters the ocean's environmental conditions, which in turn impact marine ecosystems. Some of these changes are happening fast and may be difficult to reverse. It's also happening so fast it's hard to keep up with. The identification and monitoring of such changes, which also includes tipping points, is an ongoing and emerging research effort. Prevention of negative impacts requires mitigation efforts based on feasible research-based pathways. Climate-induced tipping points are traditionally associated with singular catastrophic events relative to natural variations of dramatic negative impact. High probability, high impact ocean tipping points due to warming, ocean acidification, deoxygenation may be more fragmented both regionally and in time, but still adds up to global dimensions. These tipping points, in combination with gradual changes, need to be addressed as seriously as singular catastrophic events in order to prevent the cumulative and often compounding negative societal and Earth system impacts. So now here we go into the introduction. Substantial efforts have been made to carry out research, raise awareness of tipping points in the Earth system under human-induced climate change. By the way, you might have noticed in a lot of these papers that I've been discussing with you, the scientists are basically not pulling any punches. They're stating human-induced climate change because the consensus is among the scientists from all over the world that humans are causing what's happening to the climate and causing these rapid changes to take place because of human activity. So all these people say, well, it's still a question. Bullshit. Okay. Politicians be damned. They don't know what the hell they're talking about. When you see these papers, it's basically there is a scientific consensus. Humans are causing what's the mess that's going on. So let's just put that to rest once and for all. And they talk about, singular catastrophic events, with an extraordinary negative, right? Basically what was repeated in the abstract there, some are currently assessed as having a fairly low probability of occurring before 2100. the collapse of the global ocean overturning circulation, or the rapid partial disintegration of the West Antarctic ice sheet exemplified low probability, high impact events with severe consequences for the Earth system. Circulation changes would cause alterations in Earth's heat budget, while the ice sheet instability would cause a sea level rise of several meters. Given the considerable negative impact were such events to occur, it is wise to minimize the associated risks through greenhouse gas emission reductions now. Our focus here, however, is on imminent ocean changes that are already having or soon will have a profound impact on the marine environment, on its ecosystems, goods and services, and hence on society. So not just, we're losing the Arctic sea ice. It's not just, AMOC and the conveyor belt slowing down. It's, if we get severe stratification because of the heat in the ocean, then productivity falls off. Fish yields fall off. People will go hungry. That is an example of meaning the impacts on society. The ocean is a giant reservoir of heat and dissolved carbon. Since the beginning of the Industrial Revolution, the oceans have taken up 30 to 40% of the total carbon dioxide, 93% of the heat added to the atmosphere by human activity, right? I went over that with you, this 93% value, in my ocean heat content video. Right? So, several studies are now verifying that amount. The provision of this service to human societies comes with a high cost, as it causes the ocean to warm, become more acidic, with a myriad of consequences for marine biogeochemistry and life, including the loss of oxygen. We argue that ocean warming, ocean acidification, ocean deoxygenation, if left unabated, have the potential to trigger a number of abrupt changes from tipping points in the marine environment with potentially serious consequences for marine ecosystems and ocean functioning. I did a video talking about the CCD, the calcite compensation depth, and how that is becoming shallower and shallower. Basically, what this means is that calcium carbonate, which contains CO2, starts becoming more and more in solution. Organisms that need to make a shell, a test, what have you, that utilize calcium carbonate are finding this more and more difficult to take place. In other words, they're losing their homes, they're running around naked, makes them more vulnerable for mortality. Human-caused environmental changes can materialize very rapidly or abruptly, typically at rates much faster than sustained natural changes of the past. How many times have you heard me stress in my videos? It's the rate of change that matters. We're seeing rapid rate of changes that are faster than natural cycles, natural variations. Such changes are already ongoing and documented for ocean warming, acidification, and to a certain degree, deoxygenation. And then you take into account heat waves, coastal hypoxia, that's regions of low oxygen, ocean acidification events linked to, for example, strong upwelling episodes. Since these developments are likely to aggravate over this century, they are important, as are the extraordinary abrupt singular events. So their aim is to demonstrate there are a number of high probability, high impact tipping points in the ocean's physical, chemical, biological systems. They then go on to discuss tipping point. What is meant by that? How do you define it? And it's an interesting argument here because, once again, to a scientist, a certain term has a specific meaning, but it may have a completely different meaning than what the layperson thinks of it. For example, theory, hypothesis, or compelling data. Okay, Theory means something very specific to a scientist. To the layperson, it means, oh, just made up shit. You know, compelling data to a scientist means interesting but unproven. To a layperson, it means, oh, it's evidence to support this, and it proves it. Well, of course, scientists don't prove anything. So there can be a gap in the use of terminology, is what I'm trying to say here. And we need to be mindful of this. So the term tipping point has a long history in chemistry and mathematics, describing a qualitative change in the characteristics of a system. For example, mathematical bifurcation. Regime shifts, also called alternate stable states, are major system reorganizations in, for example, ecosystems or socio-ecological systems. Such shifts are the result of crossing a tipping point, after which the system can quickly shift away from its current state into a contrasting alternative state. The recovery to the initial system state may be difficult or even impossible. The drivers that induce a tipping point can be either a forcing or a change of the inherent system properties, such as freshwater content, bathymetry, or other system parameters. Here, and okay, now they're going to define how they're going to use it in this discussion here. Here we use the term tipping point according to the recent Intergovernmental Panel on Climate Change, the IPCC, special report on the ocean and cryosphere and the changing climate. So here's the definition. A level of change in system properties beyond which a system reorganizes, often in a non-linear manner, and does not return to the initial state, to the original initial state, even if the drivers of the change are abated. For the climate system, the term refers to a critical threshold at which global or regional climate changes from one stable state to another stable state. I would argue that the switch over from a stable state of the past or recent past will take us to not another stable state, but an unstable state due to the perturbation of the system, which prevents or inhibits settling on a new, shall we say, new conditions, a new stable state, or the new regime. Because the system is perturbed and continues to be perturbed, it cannot find its new equilibrium situation. So I make that argument here. And they do reference one. So if you want to know what reference one is, you scroll down and you look at the list of reference one. It's right here. T.M. Letton et al. Tipping elements in the Earth's climate system. And there's the publication. And that was in 2008. And by the way, this paper was written by Christoph Heinz, Thorsten Blenkner, Helena Martins, Dagmar Rusiecka, and several other authors. These are the main lead authors for this paper. So this paper, 2008, defined a subsystem of the climate system that could experience a tipping point. Unfortunately, the phrase tipping point is often incorrectly used in the environmental literature when the author simply means some threshold after which increasing damages or impacts occur, but these are not related to a mathematical bifurcation or regime shifts. In complex physical, chemical, biological, marine systems, tipping points associated with nonlinear changes in these systems relative to the forcing applied can often not be as easily identified as in the theoretical analysis of simple dynamical systems. So then they refer to, their table 6.1, and they refer to this reference here, a paper that was published in 2019. And so you can click on that, find that paper, look at their table 1 where they list major marine abrupt changes and their reversibility characteristics associated with physical chemical forcing of the ocean resulting from anthropogenic activities. Okay, so then they talk about extreme events in circulation, stratification, seawater temperature, changes both gradual and abrupt, the biogeochemical variables, basically all the, like the nitrate cycle, the phosphorus cycle, all those biogeochemical cyclings, the pathways, and so on. It can be very complicated. Tipping points in marine biogeochemistry and ecosystem can occur in the gradual physical change, while physical changes can cascade or trigger biogeochemical and ecosystem-wide tipping points. Likewise, gradual abrupt changes in biogeochemistry can induce ecosystem-wide regime shifts. So now they reference figure 1 here, so let's take a look at figure 1. I'll read you the description here, then I'll enlarge it so we can look at it. Okay, abrupt system changes in the physical, biogeochemical, and ecosystem compartments of the ocean, and referred to as the big colored boxes, can be induced by external drivers, which are the rounded black and white boxes, these guys here, okay, or by couplings between the compartments. Tipping behavior can be potentially induced by any type of boundary condition and can cascade from a change of the system state in one compartment to the boundary conditions for another compartment. System state on the y-axis of the small diagrams denotes all relative state variables, such as temperature, oxygen concentration, pH, and so forth. Boundary conditions on the x-axis includes all relative forcings, either from external sources or from other compartments of the ocean system. N sub R stands for reactive nitrogen, such as nutrient inputs from land. Okay, this is not atmospheric nitrogen. So typically this would be nitrogen in the form of nitrites, NO2, nitrates, NO3, ammonium, and H4. Okay, typical sources for nitrogen cycling in ecosystems. Both boundary conditions and system states are time dependent. Abrupt changes can potentially be reversible so that one system state occurs for a unique type of conditions directly following the forcing. I still make the argument that because the system's been perturbed, transitioning into another state and assuming that new state to be stable is most unlikely. The system continues to be perturbed so that the equilibrium state, the new equilibrium state, finds it difficult to be established. Okay, that's just my assessment of that. So let's take a look at what's going on here. So here are the physical boundary condition. So what they're talking about here is a smooth response. So in other words, a nice transition, okay, versus tipping where it's stable, something happens. This is an abrupt change, right? This would be a gradual change. This is an abrupt change, and then it leads to a new system. Now, here what they're showing is a possibility of something happens, leads to a new system, and then perhaps you could reverse it and leads back down to the original state. And they call this hysteresis, where it goes from one to the other, but it's difficult to return fully to the original state. I did a video on the ice in Antarctica and hysteresis related to that as an example, where basically that, because of all the warmth and carbon we put into the system, we cause so much ice melting that even if we were to remove all that carbon, cool the planet down, we would not be able to refreeze every bit of that meltwater. Okay. So we have the connections between the physical boundary conditions and what are some of the drivers? Radiative forcing, for example, albedo changes. So there's a link. The physics affects the biogeochemistry. or the physics could go directly affecting the ecosystem boundary condition. Basically, it's all linked together. So we see the same kind of modeling, smooth, gradual response versus something abrupt happening, and whammo, we've got a new state. So biogeochemical boundary conditions. What are some of the biogeochemical drivers? CO2, pH, nitrogen input, dust deposition, changes in oxygen solubility. Okay, you heat up the waters. That's a physical forcing. Oxygen solubility in the ocean decreases. Okay. And then you have ecosystem boundary conditions. Again, the same thing here. So what are some of the drivers for ecosystem boundary conditions? Overfishing, invasive species, biodiversity loss, upsetting the interaction of the organism. But if you change the concentration or the pathways of the various chemical species, that could affect how the organisms respond to that. If you change the physical parameters, you can directly affect how the organisms respond to that. Or the physical parameters affect the biogeochemical parameters, which then affect the organisms and the ecosystem. So it's all tied together, and any one of these things can change and result in a new state. It's basically what this is. This is a model representation to give you an idea of what's happening. Okay. We will present here the evidence of high probability, high impact tipping points in ocean physics, chemistry, and biology, the challenge of dealing with this, and then options for mitigation measures to avoid future tipping points. Okay, so ongoing ocean change and tipping points. Tipping points can be reached, for example, for certain degrees in warming, a certain decline of marine dissolved oxygen, or a certain change in acid-base chemistry through CO2 uptake from the atmosphere. So in other words, the waters absorb CO2, you decrease the pH, right? So you're changing the acid-base relationship, and the increased acidity could lead to things such as the shells of organisms dissolving. Okay? So let's look at warming. Each species of marine organism has an optimal temperature window. You've heard me discuss that numerous times before for its physiological functioning. Most organisms are vulnerable to warming above this optimal temperature because basically their metabolism speeds up and they could literally metabolically burn themselves out. Okay? Typically, they do tend to be less vulnerable toward the cooling. So, first of all, cooling slows down the metabolism, and so they do better in cooler than optimal conditions than warmer than optimal conditions. Okay? Reference 26. Okay, a whole pile of people here. Paper written in 2018, and it's basically impacts of 1.5 degrees C global warming on natural and human systems. And it's a part of a consortium there. And they conclude with high confidence that the majority of tropical coral reefs that exist today will disappear even if global warming is limited to 1.5 degrees C. Basically, we're seeing that now with the bleaching of the corals, but also the increased acidification is dissolving the corals. These coral reef systems play an important role for fisheries, coastal protection, fish nurseries, for a number of other ecosystem services. The effect of ocean warming extends far beyond the most sensitive marine organisms, with range shifts being observed across the food web from phytoplankton to marine mammals. Okay, I just did a video where I talked about how marine species are shifting. They're moving from, say, tropical waters to subtropical waters, to temperate waters, and so forth. And temperate water species are moving to subpolar. I've done videos of that in the past. As in the past, there's also the potential for unexpected climate-related regime shifts in the marine ecosystem, such as those observed in the North Pacific. Deoxygenation, this is a biggie. Most marine organisms can only exist in seawater with sufficiently high concentrations of dissolved O2. Warming of the ocean decreases the solubility of oxygen in seawater. Further warming induces an acceleration of metabolic rates and thus also of oxygen consumption. Kind of alluded to that. A slowing down of ocean mixing under warming transports less oxygen from the surface into the ocean interior, changing the balance between oxygen supply and consumption. Basically, as we stratify the oceans, vertical movement, vertical transport of oxygen, carbon, nutrients, what have you, and that's up and down, by the way, is limited. So an organism at depth may not be getting that oxygen needed. And also, if you have an organism such as a tuna, a marlin, a great white shark that are homeotherms, they need higher oxygen levels. If the DO level, dissolved oxygen level, decreases, they may not get enough oxygen sufficient to run their metabolism. They basically start suffocating. So there are a lot of implications with this. In addition, delivery of land-based nutrients through runoff, agricultural fertilizers, domestic waste, and deposition from the atmosphere increases biological productivity in coastal areas, disrupting ecosystems, enhancing the risk of coastal hypoxia. This, what they're basically referring to, is eutrophication, where you throw in so much of the nutrient, you cause algal blooms. And then the algal blooms basically result in the oxygen levels tanking. These factors cause O2 drawdown in the ocean with potential for large consequences in combination with warming from marine organisms, whose species distribution, growth, survival, and ability to reproduce are negatively affected. Current O2 minimum zones would dissolve O2 concentrations lower than 80 micromoles per liter. That's what this all means, okay? Micromoles per liter, right? Which is close to the threshold of 60 micromoles per liter, below which waters become dead zones for many. They say higher animals, I would say animals that require higher metabolic rate. And these are expected to extend under climatic change if greenhouse gas emissions rise unabated. Ocean deoxygenation is sensitive to the magnitude of radiative forcing by greenhouse gases and other agents and can persist for centuries to millennia, right? Centuries to thousands of years. Although regionally trends can be reversed. Specific heat of water. It takes a long time to remove that extra heat. 200 plus zetajoules worth of extra heat. Transiently, the global mean ocean oxygen concentration is projected to decrease by a few percent under low forcing to up to 40% under high forcing, with deoxygenation peaking about 1,000 years after stabilization radiative forcing. So there's that extending for for a very long time. Hypoxic waters will expand over the next millennium. Recovery will be slow and remains incomplete under high forcing, especially in the thermocline. And then T.L. Frolicher, in a paper in 2020, contrasting upper and deep ocean oxygen response to protracted global warming. Okay, and then they conclude this paragraph with mitigation measures are projected to reduce peak decreases in oceanic oxygen inventory by 4.4% per degree Celsius of avoided equilibrium warming.
So this concludes part 1 of this 2-part Ocean Tipping Point video series. Part 2 will continue from this point forward, where I start discussing what the researchers talk about with respect to ocean acidification. Stay tuned.
Hello folks, this is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.